I had to write a Python code to find the SVD that comes out more simply. Usually if you just write down any matrix and do this SVD, you can do SVD for any matrix. However, if you try to do it by hand, it'll be very messy. So this comes out as relatively doable. Still, it's very ugly, but it's doable compared to other ones. Right? So let's try to do this one. So solution. So the idea of the singular value decomposition is to use the spectral theorem, which says that if you have a symmetric matrix, you can diagonalize it using unitary matrices. So you have to use it, but this is not symmetric. How do you get a symmetric matrix? If I call this as A, then if you take A star A, where star means you take complex conjugate and you take the transpose. Since all these numbers are real, the complex conjugate doesn't do anything, so the only thing that's being done is just taking the transpose. Now when you do the transpose, the diagonals stay there, so these don't change, but then 4 and 2 will switch places, and 3 will go over here, 2 will go over here. So what you get is you end up with 3, 2, 3, and 4, negative 3, 2. And then 3, 2, 3, 4, negative 3, 2. So you make this. And the way I think about transpose is really, it takes column vectors into row vectors. So look at this column, 3, 2, 3, which was a column vector, now became a row vector on top. Okay? So we do the matrix multiplication. 3 times 3 is 9, 2 times 2 is 4, 3 times 3 is 9. So what's that? 18 plus 4, that's 22. And then if you do this times this, 3 times 4 is 12, 2 times negative 3 is negative 6, 3 times 2 is positive 6. Negative 6 and positive 6 cancel away, so you just get 12. And then again, this times this is same as the same calculation as before, right? It's a dot product is commutative, so whether you do the vector 4, negative 3 times 3, 2, 3, same as 3, 2, 3 times 4, negative 3, 2. So you're going to get 12 again. You can check that you get the same answer. And then finally, this one, this times this, 4 times 4 is 16, negative 3 times negative 3 is positive 9, 2 times 2 is 4, 4 plus 16 is 20, plus 9, that's 29. Okay. So that is the matrix that you get. It's a symmetric matrix. And you just diagonalize this as you would diagonalize any matrix. You find eigenvectors and you use that as the new basis, and it makes a matrix diagonal. The only difference is that because we know that for symmetric or Hermitian matrices, eigenvectors with distinct eigenvalues are orthogonal. When you diagonalize this, you can make the diagonalizing matrices P and P inverse to be rather orthogonal matrices. So we can continue after that, right? So let's do this. We now, so step 1 is now step 1, diagonalize A star A using eigenvalues and eigenvectors. Okay. And here, eigenvectors should be normalized, so that the end result is that your eigenvectors form an orthonormal basis. Right? Okay, so let's find the determinant of 22 minus lambda, 12, 29 minus lambda, and saying this equal to 0 gives you the eigenvalue equation. So it's going to be lambda squared. 22 plus 29 gives you 51, so it will be negative 51. And then, so one formula for this is that whenever you do A minus lambda, B, C, D minus lambda, the determinant of this, this turns out to be lambda squared minus the trace of A, trace of this matrix, times lambda plus the determinant of A. So I'm using this shortcut. You could multiply it out, but this is way faster. That's how I could do all this calculation in my car while driving here. Yeah. Okay. So right. So I actually had to do this in my car. 22 times 29, mental math. So the way I did it was 22 times 30 minus 22 times 1, right? 30 minus 1 is 29, right? And that's 660. And then minus 22, so that's 638. Okay. And I had to double check that several times in my mind just to make sure that it's correct. So it's 638. Minus, you have 12 times 12, which is 144. Okay, so that's the determinant of this matrix. 22 times 29 minus 12 times 12. That's the determinant. And therefore, what I get is, let's see, lambda squared minus 51 lambda. What is that? That's 494, right? 494, okay, plus. Okay, so now in order to factor this, I have to factor this to solve it, right? And by the way, I did this in Python yesterday, so I know that the lambdas are going to be integers. So it's not going to be some crazy numbers. It has to be integers, except that numbers are a little big. So what I need to do is I have to find two numbers that add to negative 51 and multiply to 494. So I have to factor this. And you have to know that I'm doing all this in my car while I'm driving. Right, so it's 2 times 494 is 2 times 247, right? Okay. And then 247 is a product of two things at least. It has to be, because there's no way you could get 51. But I know that this is not divisible by 3, because 2 plus 4 is 6. 6 plus 7 is 13. 13 is not divisible by 3. So this number is not divisible by 3. So, and it's not divisible by 5. It doesn't end with 5. It's not divisible by any even number. So if it is divisible by some number, it has to be not even 7, because this is divisible by 7, but 240 is not. So it has to be something 11 or more. That's like too much for while trying to drive in the car. So in my mind, this is what I did. Okay, so 247 must be 256 minus 9, right? Mm-hmm. So that is 16 squared minus 3 squared. So that's 13 times what? Or no. 16 minus 3 times 16 plus 3, right? Yes. So it's 13 times 19. So I know that this is 2 times 13 times 19. Okay. And then now what you do is, 2 times 19 gives you 38, and 38 plus 13 gives you 51. Great, it works, right? So I know that 38 and 13 are the two eigenvalues. Okay, so we now have this as lambda minus 38. Let me write 13 first. 13, and then lambda minus 38. Okay. This plus this gives you negative 51. This times this gives you that. Okay, now we have to figure out the eigenvectors. So for case 1, lambda equals to 13. So that's going to give you 22 minus 13 is 9. And then 29 minus 13 is 16. Times AB has to be 0, 0. And I know that this is a degenerate matrix, so you just have to calculate the top and find this integer that would make the top 0. So 9 times A plus 12B has to be 0. And since this is divisible by 3, so let's divide everything by 3. So it's 3A plus 4B equals to 0. So that A is 4 and B equals to negative 3 would work. Okay, so I see that the eigenvector in this case would be associated with A is 4, B is negative 3. Okay? Secondly, for lambda equal to 38, let's see what happens if I put 38 there. 22 minus 38 is negative 16. 12, 12. 29 minus 38 gives you negative 9. Again, this is a degenerate matrix, so the second equation you get will be the same as the first equation you get, so we just write down the first equation. Negative 16a plus 12b equals to 0. You divide everything by 4. And I see that if a is 3 and b is 4, then it's negative 12 plus 12. So 3 and 4 would work. So for this one, we have the vector 3 and 4. Now, the great thing about these vectors, the reason my Python program that generated nice examples gave us this one was because the eigenvectors themselves are really easy to normalize. So what is the norm of this matrix? 4 squared is 16, 3 squared is 9. That's 25 square root of 25 is 5. So the length of these vectors are both 5s. And therefore, if you divide by 5, these are unit vectors. Okay. Moreover, if you do a dot product between these two, if you do a dot product, it's 4 times 3 plus negative 3 times 4. What do you get? Plus 12 minus 12, you get 0, which means these two vectors are orthogonal. Okay. So this calculation shows you, so here's what we figured out so far. This calculation shows us that if you have this matrix 22, 12, 12, 29, and if we multiply it by 4/5, negative 3/5, and then 3/5, 4/5. I had the 5 pulled outside, but if I bring it inside, it's 4/5, negative 3/5, 3/5, and 4/5. Then this times this is 13 times this vector. Right? Whereas, so it's 13 times this. If you multiply this matrix with this, this is only going to multiply 13 to this one, so that it's going to match this times this part. And then if you multiply this with the second eigenvector, this eigenvector has the eigenvalue 38, so it will be 0, 38. Okay? And then here you write down 3, 5, 4, 5. So this is nothing more than a summary of the two calculations we've done. This times this vector is 13 times this vector. This times this vector is 38 times this vector. That's all we have. Right? But that is the diagonalization, because see, here is the diagonal matrix. This is the orthogonal matrix. So you can multiply. See, orthogonal matrices have the transpose itself as the inverse matrix. So if I multiply the transpose of this, both sides, so that this cancels and you get the other sides, you get 22, 12, 12, 29 equal to 4/5, negative 3/5, 3/5, 4/5, 13, 0, 0, 38, and then 4/5, negative 3/5, 3/5, 4/5, star. Really, star is just transpose, okay? Yeah, and even the transpose is easy. It's just switching these two around. Okay. All right, so that is the diagonalization of this matrix, right? But on the other hand, that was a step 2, step 1. In step 2, what you have to do is you have to compute what the original A does to these eigenvectors. Okay? So step 2, compute A times B for each eigenvector V. Okay. So let's do that. Here's 3, 4, 2, negative 3, 3, 2 times the eigenvector. Let me pull the 1/5 out because it makes things easier. 1/5 of 4, negative 3. Let's see what that gives us. Okay, 1/5 can be pulled outside, and we can just do the integer multiplication. 3 times 4 is 12, 4 times negative 3 is negative 12, so you get 0 on the top. 2 times 4 is 8, negative 3 times negative 3 is 9, 9 plus 8 is 17. 3 times 4 is 12, 2 times negative 3 is 6, so you get 6. Okay. And then, for the second one, 3, 4, 2, negative 3, 3, 2. The next vector is 1/5 of 3 and 4. So let's see what that gives us. 3, 4, 3, 4, that's going to give us 25. Because 3 times 3 is 9, 4 times 4 is 16, 16 plus 9 is 25. 2 times 3 is 6, negative 3 times 4 is negative 12, so it's negative 6. 3 times 3 is 9, 2 times 4 is 8, 8 plus 9 is 17. So you get these vectors. And if you recall the proof that every matrix has a singular value decomposition, the idea was just take these eigenvectors, apply A to it, and the outcome will again form an orthonormal set, an orthogonal set. Okay? So what you see is that this thing here and this thing here, if you do a dot product between these two vectors, you get 0. Let's check that. 0 times 25 is 0. 17 times negative 6, whatever that is, but here it's 6 times 17 with positive. So if you do the calculation of the dot product, you get 0. So these two are indeed orthogonal to each other. Okay? So, and then what you have to do is, now you have to make these normalized as well. So let's try that. What is the norm of 0, 17, and 6? Well, that's 0 squared plus 17 squared plus 6 squared square root. 17 squared is 289. By the way, I have those memorized. So you have 289 plus 36. It's going to give you 325 square root. And then, because this is 25 times 13, you can pull a 25 outside the square root as 5. So this becomes 5 times square root of 13. And what that means is that if you take this, if you use this 1/5 in front, that just introduces 5 in here, so that this vector with the 1/5 in front will have square root of 13 as its size. Okay. And let's see. Okay, so we'll
that would be the unit vector, right?
yeah. So once you divide this by this, you get a unit vector, right? Okay. And then you can do the same thing for the second one. For this one, if you do 25 squared plus negative 6 squared plus 17 squared, well, this we already know it's 325. This is 625, so it's square root of 950. And then this is 25 times 40 gives you 1,000, but then this is two quarters missing from. So I'm in my mind, I'm thinking like you have $9.50, and you're thinking, of how many quarters is that? Okay. So $10 is 40 quarters, and then you're missing 2 quarters there, so it must be 38. Of course, we can all do this with a calculator, but I'm describing this as if I was like driving here and then I'm doing everything in my head. Okay? So this is what I have. This is like 5 times square root of 38. And therefore, if you include the 5, then this as a whole would be having square root of 38 as its norm. And therefore, if you divide this by square root of 38, then it's a unit vector. All right, so let's see where we are at so far. Oh, and by the way, you should notice that this square root of 13 and square root of 38 are really the square roots of these numbers, and it's not a coincidence. These numbers are called singular values. Okay, so a matrix, a square matrix has eigenvalues, right? But even if it's not a square matrix, you can still define something called a singular value, which is you make it into a symmetric matrix by multiplying by its adjoint, and then find the eigenvalues. The eigenvalues will always be non-negative. If you make a symmetric matrix out of something like this, it will always be positive semi-definite, so that the square roots of the eigenvalues will always be able to be computed as a real value, and those will be called the singular value of a matrix. All right, so that's the end of step 2. Let's see what we have so far. Let's write down what we have so far. So if I put this result and this result side by side, so here I have 3, 4, 2, negative 3, 3, 2, multiplied by 4/5, negative 3/5, 3/5, 4/5. This times the first vector gave us this vector, right? But to make it as a unit vector, you have to divide by square root of 13. So it's really 0, 17 divided by 5 square root of 13, and 6 divided by 5 square root of 13. So this, this times square root of 13. So see how things work out here. If you multiply this to this matrix, then only the first column will be multiplied by square root of 13, canceling these two, square root of 13, and what you have now is exactly this vector, which is the result that we got in the first calculation, right? And then for this second one, what was it? It's 25, negative 6, 17. Those are divided by 25 over 5 times square root of 38, negative 6 over 5 times square root of 38, and then 17 over 5 times square root of 38, and then this will be multiplied by square root of 38. Okay, so that's what you have. And see, already this result looks pretty similar to singular value decomposition, except that we are missing just one more piece. But I still want to say what we achieved here. So here's what we did. We were able to write this matrix as this times, and you can move this to the right side. How do you move this to the right side? Dividing means multiplying by the inverse, right? What's the inverse of an orthogonal matrix? The adjoint, you're right. Okay, so adjoint, which is the star. If you take the conjugate star, you get the inverse. So if you move this to the right side as the star, then the usual singular value decomposition, which was, what's the form of singular decomposition? It's A equals to U times the diagonal times V star, where U and V must be orthogonal for real case and should be unitary for complex matrices. And diagonal is a diagonal matrix. So you have almost everything. If you move this to the other side, you definitely have orthogonal adjoint. And that is the diagonal. Except that this U has to be an orthogonal matrix. Orthogonal matrices have to be a square matrix, but it's not a square matrix. Okay? For a matrix to be orthogonal, it has to be built with orthogonal basis elements. But this is three-dimensional, so what do we need? We need a third column that's perpendicular to both of these. Okay? And if we add an extra thing to this, then it will be perfect. So step 3 is to actually come up with so maybe I should note that these are orthonormal. So first it's normalized. These are unit vectors by themselves, and they're orthogonal to each other. Okay? So we just need to find the third vector to form an entire basis, which is orthogonal to both. And one way to do to find the third vector would be to do something called Gram-Schmidt process. So it's easy to see that 1, 1, 1 is not in the span of these two vectors, and so you take 1, 1, 1 to make a basis, and then if you have any basis, you can use Gram-Schmidt to get that last basis element to be orthonormal to everything else. But when I tried to do that in my head, I just realized it's just too much. So we'll take the easy way out. But this easy way out will only work because we're in the three dimensions. If you have two vectors in dimension 3, you can always find the perpendicular vector, the third one, easily by doing what?
Unit determinant? Or the cross product.
Cross product, right. So what we're going to do is we're going to take 0, 17, 6, and 25, negative 6, 17. So 0, 17, 6, this vector, and 25, negative 6, 17, I, j, k. Oh, sorry, I forgot to write step 3. Okay, so I should write step 3. Step 3, extend the orthogonal vectors A, V, right? These vectors that we obtained by multiplying A times the eigenvectors, yeah, to a orthonormal basis of whatever. Okay, so this is dimension 3. To get an orthonormal basis, we need the third element. And to do that, we will have to use the cross product. So I, j, k, and you have 0, 17, 6, and then 25, negative 6, 17. And then that gives you I times as 289 plus 36, which is 325 I. Then for J, J requires the checkerboard of signs for determinant requires a minus in front. Okay? And it's 0 times 17 minus 6 times 25, but there's a minus in front before, so 6 times 25 is 150. Okay, then finally, plus k. If you choose k, this is this times this minus this times this. So you have 17 times 25. Oh, with the minus. Okay. All right, so what's that? 325i plus 150j minus 17 times 25.
425.
Yeah, but I don't want that because, see, every one of these are divisible by 25, so I'm going to just take the 25 out. And this is 13 times 25, this is 6 times 25, and this is negative 17 times 25. So this vector itself will be perpendicular to both of these vectors. Okay? We don't need the 25, so we just have that vector. Okay, so we got a perpendicular vector, and now all we have to do is to take this vector and normalize it. So what do you get if you normalize it? 13 squared plus 6 squared plus 17 squared, 169 plus, I remember this being 325. So what is that? 494. This also looks familiar. It was something that we got earlier. It was 2 times 13 times 19, right? Or 38 times 13. Okay, anyways, so that's what you get. So the size of this vector is the square root of this. This unfortunately doesn't have any square factors, so that's all it is. So here's what I got. The conclusion of this is that if you build a matrix that's 0, 17 over 5 radical 3, 13, 6 over 5 radical 13, and then 25 over 5 radical 38, negative 6 over 5 radical 38. I'm just copying that vector here. 17 over 5 radical 38. And then I augment that with this new vector that we obtained, which is 13 divided by square root of 494. And then the next one is 6 divided by square root of 494. And then 17 divided by square root of 494. This will be, the columns will make up an orthonormal basis. So that overall, this will be an orthonormal, orthogonal matrix. Okay, so this will be, see, our goal is to make A as U, D, V star, right? And now we found our U. That's our U. Okay. All right. So now we are ready to write down the answer. Since I don't want to write this twice, forgive me for just reusing this, but the final answer will be like this. The final answer, the singular value decomposition of 3, 4, 2, negative 3, 3, 2 is going to be this one times this thing in the middle, square root of 13, 0, 0, square root of 38. But wait, if I just stop here, then the product of these two matrices are not defined, because if you try to do this times this, you have 3 elements, but this only has 2 elements. So to make it work, you need to put an extra zeros at the bottom. Okay. Now, we want zeros because this shouldn't really matter, right? See, if you in 3D, if you have two vectors that are orthonormal to each other already, then there are actually 2 directions that's perpendicular. It could be this one or that one. So in a sense, singular value decomposition is not unique. You can choose this one or that one. I could replace this by the negatives of this. Oh, by the way, I forgot to put a minus here. I could take this one and put a minus, and then it will still work. Okay? But because the final answer shouldn't be really using this one, I put 0, 0 for that. And then the other vector, what is this? 4/5, negative 3/5, 3/5, and 4/5. And you do that, and that is the final answer for the singular value decomposition. Oh, I should put a star here. Okay.